Okay, thanks. So thank you for having me here. Today I'll be talking about working a project with Shachar, which is about norms that are defined by systems of linear forms. First, we will go through some notions and tools that we'll be using during the work, and then later we will define what do we mean by these generalized norms that we study and present a characterization for them and study the topologies that they provide. And during the talk, since my brother, most of you should probably know my brother, and we will use a lot of results which are by Hamed and Shachar. To just not to make it confusing, I will use his full name whenever I refer to his results. So it is often we are in study of mathematical objects such as functions, graphs, and hypergraphs. We are usually interested in distinguishing between structure and randomness. So namely, we define a set of structured functions such as linear functions or bounded degree polynomials or characters over the Boolean cube. And we are interested in the case to distinguish between structured functions and functions that are far from having structure. And we call those uniform functions. For example, functions that are not correlated with linear or cubic functions, or in the case of characters, functions that have small Fourier coefficients. These uniform functions usually are also referred to as pseudo-random, and the reason for this is that usually there's not many structured functions, so a random function would act as uniform. It has been seen many times that these notions of uniformity are useful in the study of dense objects. For example, Gowers in '98 defined this new notion of uniformity for complex functions over abelian groups, which later was used by Green and Tao to prove the existence of arithmetic progressions of arbitrary length in primes. So now we will define the Garrisons norm and look at some of its properties. So for this part of the talk, we will assume that P is a fixed prime, and we will be interested in complex functions over FPN. And we'll define the inner product of two functions as the average of F times conjugate of G. And the Fourier analysis over FPN, just as a short reminder, we can write a function F as a linear combination of characters, where characters are we will use this notation for e to the 2 pi I x over p. And the coefficients are just the inner product of F with the corresponding characters. So now we're ready to define the Gowers' uniformity norm. So for a complex function, the case uniformity norm of Gowers of F is defined by the following average. So what we do, we pick a random k-dimensional cube in FPN, and we look at the values of F on the points of the cube. And this c to the k minus s is just adding the proper conjugations. So as an example, the U2 norm of F is defined by the following average over the product of 4 points in Fp to the n. So now that we know the definition of Gowers' norm, we can define our structured functions to be these set of what we call phase d polynomials, which are basically exponentials in polynomials of degree d. And we can ask the question, does Gowers' uniformity norm actually capture uniformity against these structured functions? Well, the answer turns out to be yes for large characteristics when p is larger than the degree. And in a series of work, Bergelsen, Tao, and Ziegler, prove that the ud plus 1 captures uniformity against the phase d polynomials. So to see this, to make some sense out of this, we can look at what does Gowers norm do to exponential functions of polynomials. It turns out that if we take the kth Gowers norm of the phase p polynomial, then what it does is it takes the kth derivative of the exponent, where the derivative is the discrete additive derivative, which is defined as following. Well, now that, so let's look at an example. What happens, we can actually rearrange the Gowers norm of p of x, the second Gowers norm, as following, which is basically the second derivative. Well, now that we know this fact, and we know that a polynomial of degree k will always have a k plus first derivative that is equal to 0, and this fact is independent of the directions that we take the derivative and the point x. So what this immediately tells us is this invariance result, that if we multiply a function f by a phase k polynomial, it will not change the k plus first Gowers norm. Another very useful fact about Gowers norm is that it obeys this Gowers-Cauchy-Schwarz type inequality. What this says is basically if we pick 2 to the k different functions and look at a random cube, but instead of just looking at the value of the same function, on each point we use the corresponding function on it. We can bound this by the product of the kth Gowers norm of each individual functions. This has a very immediate corollary to it, which says that the average of a function is bounded by its kth Gowers norm. And how we would get this is just we will make the f empty to be equal to our f and the rest of the functions to be the constant 1 functions. So now to add up what we just saw, we can see that the inner product of f with a phase k polynomial is equal to this average, and this is we just saw by the Cauchy-Schwarz inequality that this inequality holds, and because of the invariance, we have the last equation, and this is basically called the Gowers direct theorem. What this says is that if the Gowers norm, the k plus first Gowers norm of a function is small, then if f does not correlate much with the structured functions that we just picked. It turns out that the inverse is also true, but again with the assumption that d is less than p. So what it means is that if the supremum of the inner product is small, then we can actually say that the Gowers norm is going to be small. So next tool that we will use is going to be called this thing called higher degree Fourier analysis. Notice that in the original Fourier analysis, we have these vectors coming from FPN, and for each of them we have these characters which are exponential in linear functions. And in higher degree Fourier analysis, we want to replace these exponents with higher degree polynomials. But it's not that obvious. Why can we do it? And if we can do it, why is it useful? Can we do it in a useful way? A series of theorems that, again, we will use are called the decomposition theorems. And decomposition theorems, it's a natural question to ask, and it can be very useful when we study an object. We want to decompose it to a random part and a structured part. And since we can study it's easier to study structured functions or the random functions, then it can help a lot in the study of the original object. So we want to decompose it to structured and pseudorandom. Let's see what does it mean in the Gowers uniformity setting. So we know that pseudorandom now means it has small Gowers norm, and structured means that it is a function of a few phase d polynomials. Well, it turns out that we can do it for every function. So given a d less than p and a positive epsilon, we can decompose a function to 2 functions where the f2 has small Gowers norm, and f1 is a function of a few polynomials, where this c depends on the epsilon, only on the epsilon, and it doesn't depend on that.
What kind of function is it? Polynomial or
any function. So it has to be from fp to the c to the.
How does c depend on epsilon?
Oh, it's a terrible. It's like powers of. So now that we have the decomposition theorem, notice that the f2 we can just omit looking at f2 because it has very small Garrisons norm. It is the random part. And if we just look at the f1, we can use the Fourier decomposition of f, the capital F, and write this sort of higher degree Fourier decomposition, where now our characters are sort of the higher degree, the degree d polynomials. But is this useful? In the Fourier analysis, we use a lot of nice things that we can say is coming from the orthogonality that we have for characters, but it's not necessarily true for higher degree polynomials. So we actually need some sort of orthogonality of these higher degree characters that we have to be able to use the higher degree Fourier analysis. So to talk about this, we will first define the bias of a function to be just the average of this exponential function. And we will call a polynomial to be regular if it has small bias. So namely, if we call it epsilon regular if the bias of it is less than epsilon. And we call a set of polynomials to be regular if all the linear combinations are regular. So Green and Tao prove that we can actually assume in the decomposition theorem that the polynomials that we get are actually regular. So this helps us, this gives us the orthogonality that we need because all these non-zero combinations will actually have very small average. So we can say things like Parseval identity, but now things are approximately equal. Hamed and Shachar prove the following theorem. They prove that we can decompose a set of multiple functions using the same set of polynomials. And in addition, we can assume that the polynomials are homogeneous and they have very high rank, where the definition of rank is, again, a little bit technical, but we say that the polynomial has high rank if we can't write it as a function of lower degree polynomials. And this combined with the result by Kaufman and Lovett that says that large rank essentially implies small bias. Actually, this is the formal way to say it. This actually implies strong orthogonality in the decomposition. And again, we will use this. This is going to be a theorem that we will later. So the strong orthogonality will be every non-zero linear combination is going to be very small.
By the rank of
we say that a polynomial is of high rank if we can't write it as a function of few lower degree polynomials. And so now we can move on to definitions of systems of linear forms, and so that we can define the norms that we're looking at. We define a linear form L in k variables to be a vector in fp to the k. And we will use it as a function acting on fp to the n to the k. Basically, what it does is picking k vectors from fp to the n. It's L of x, how it acts is just takes the linear combination of them coming from L. Okay? And we call a set of linear forms in k variables the system of linear forms. So for example, if we let L1 to be the 1, 0, 1 and L2 to be 1, 1, 1 vectors, then this is how the equalities that we get. So Hamed and Shachar again prove a similar orthogonality, but now over linear forms. It's a stronger type of orthogonalities. So they prove that if we have a set of linear forms and a d and a positive epsilon, and we have a set of homogeneous polynomials of high rank, actually every linear combination of pi of lj's, these are now different polynomials, we'll actually, again, have this strong orthogonality property. So if there is no cancellation, the bias of these linear combinations will, again, be small. Okay. So now we have these PIs of LJs, and there is many of them. There is, in fact, K times L different polynomials that we get. And they prove that every non-zero linear combination will, again, have small bias. This will be a result that we will use in our proofs. Now we can move on to define the averages that we will be studying. So one is often, sorry? Uh-huh.
You say homogeneous polynomials. Are you also assuming that any linear combination of them also has high rank?
Yes, so we define a set to be of high rank if every linear combination is of high. Yes. So notice that the result by Kaufman and Lovett already says that every linear combination of these will have small bias. But now we're interested in the linear combinations of this form, not just PIs of X. So we will be interested in average. One is often interested in these type of averages where we are given a set of linear forms, and we're looking at the value of f over these linear forms. So for example, and we will, during this talk, we will just omit talking about conjugations. We will assume most of the times that f is a real function. So let's look at an example. If we have a real function and we define our linear forms to be this, the average T sub L of f becomes basically the Gowers' U2 norm. And if we look at a subset of FPN and we pick a characteristic function of A, and we define the linear forms to be the 1, 0, 1, 1, and 1, 2, then we will get the density of three-term arithmetic progressions in A. And notice that one can just generalize these two examples that I gave and obtain higher degree Gowers norm and a density of longer arithmetic progressions. So now let's see. So in this talk, we will be interested in such averages, but with the extra assumption that they're actually norms. They have the norm properties. And we will actually look at a more general case where, in fact, we have some non-zero, non-negative powers in these linear forms in our averages. So in the previous example, all the powers were 1. So again, for simplicity, we will not look at the conjugation. So this is the type of averages that we will look in this talk.
For what system of linear forms and what coefficient, exponents here, is this actually a norm?
Sorry?
For what?
So that, we don't have a like complete characterization for such norms. We will assume that they're norms, and we will try to see give some necessary conditions on it, and then study its properties. But for example, Gowers norms and the LP norms are examples of these.
Also in the graph norms, so that it's not.
It looks like a graph test almost.
Yes, that graph is what is the additive setting. The reason that it's not known when those things are norms or when those things are always negative or positive. It's not known how to characterize those things.
Yeah, so that's a big open problem
Is
there.
there a nice necessary condition that captures things outside of Gowers norm and LP?
Don't do that. But
Somehow in this work, we actually show that they are necessarily either similar to LP or they're similar to Gowers norm.
So you don't understand how you get a norm. If somehow you got a norm, then you can characterize a norm that you got.
Okay, let's try it this way. What's not a norm?
Almost anything you take would not be a norm.
Okay.
Yeah. So again, examples of these norms are the LP and the Gowers' norms. So what we prove is that if given a set of linear forms and a set of non-negative powers, then if we have this, the average provides us with a norm, then it has to be either of this type or of the second type, where notice that it is very important that these absolute values now appear. And the first case is when all the powers are the same, and they're greater than or equal to 1. And the second case is where all the powers are 1, and we don't have absolute values. And notice that as we just discussed, the Gowers' norm is is a norm of the second type, and the LP norms are a norm of the first type. So we call the first type norms to be the type 1 and the second ones to be the type 2. How we prove it is we prove it using a holder to prove we prove a holder type inequality, which is very involved, and I won't talk about this today. And we will use that to give the characterization. But what I can give here is that we actually show that a similar inequality to Gowers-Cauchy-Schwarz actually holds for a system of linear forms too. So if we have a set of linear forms, and we have a set of different functions and look at fi's of L, i's of x, we can actually bound this by the norm of individual functions. And so the proof idea for this is we assume that there is a set of functions that does not obey the inequality, and we normalize them and boost up the inequality until we get a contradiction with triangle inequality for the norm. So now we can focus on the main results of the talk. We will look at type 1 and type 2 norms and see what type of topology they provide. So for the study of the type 2 norms, we have to make some extra assumptions. And I mean, this is still a working project, so we'll hope to get rid of some of these assumptions that we make. But we will make the assumption that the system of linear forms is affine, which means basically the first entry in all of our linear forms is going to be 1. This is a natural assumption because most of the times we are actually interested in such averages, such as Gowers norms, or when we are looking at the density of arithmetic progressions. We want to look at the average from a base point x. So these are the assumptions that we make. And another assumption is that we have to make is that the Cauchy-Schwarz complexity, this is again another definition that I'm throwing without explaining, is just basically some number relating the dependencies between the linear forms. And later we'll see why do we have this. This is because of we have to use some results by Green and Tao and the result of Hamed and Shachar that have dependency on this. So let's see, what do we prove? We in fact prove that if for a sequence of functions over different fp to the n i's, if the limit of the norm t is 0, then it is equivalent to the L1 norm to be 0. And for type 2 norms, we prove that there is some k, that if this limit is 0, then the limit of the Gowers norms is going to be 0. And notice that now these dimensions are changing. So what we have to basically prove is that if the t norm, the type 1 norm of f is small, it is equivalent to L1 of norm being small. And this has to, the epsilon deltas should not depend on n to be able to prove that strong limit equivalence. And for type 2 norms, again, giving those assumptions that we have to make, we prove that for some k, the L norm is going to be equivalent to the Gowers' k plus first norm. Okay? So let's, type 1 norms turns out to be easy to handle. So first, let's take a look at them. And we won't go through the proof for this because it's not of main interest. So we basically prove if there is some delta of epsilon, if the norm is smaller than delta, then the L1 norm is small. And this can be handled by the holder inequality that we prove. And the nice property of the type 1 norms that we have these absolute values around f. And the second direction will actually be just easy to prove by just the Cauchy-Schwarz inequality, and not our Cauchy-Schwarz, just the famous good old Cauchy-Schwarz. So let's now look at the type 2 norms. So just as a reminder, the type 2 norms are just these type of averages, which the powers are 1. We need to, again, make some technical definitions to be able to define what type of k we will find for the equivalence to the kth Gowers norm. So for a linear form, we define its dth tensor power to be the vector that is just provided by all the possible combinations of d entries of L. So if we look at an example, if L is just a 1, 2 vector, then the second tensor power of L is going to be all these combinations that we get, which is just the 1, 2, 4, 2 vector. And another thing to note, sorry? Yeah, so all the combinations. So it's going to be on k to the.
I guess you do the first 1 times 2 is probably 1 times.
Oh, yeah. OK, sorry. Type. And it turns out that if we assume this affine, the property of being affine, actually L, for example, will appear in L squared and in L to the 3 and so on. This is something that we will use later. So again, this is a reminder of the assumptions. So we will define, for a set of linear forms, we will define Z of L to be the largest D such that this equation holds. So all the dth tensor powers sum up to 0 vector. OK? And again, given that the assumption that all these linear forms are affine, this would imply that for all d less than, for all smaller powers, this again holds, because all of them appear in the dth tensor power.
Is it obvious that D is finer?
It's not that immediate, but it can be shown. If we assume that the Cauchy-Schwarz complexity is less than p, that sort of implies.
Does that follow from this being a finite D?
I mean, it might just circle. I mean, it can be just we have p1s, and you can take any powers of them, and it will still stay 0, right? So you need some assumptions on the complexity of the linear forms. So now, having defined this Z, we can present our results. The first direction says that if the L norm of F is small, then the Z plus first Gowers norm is going to be small. And the second direction is that if the Z plus first Gowers norm is small, then the L norm is going to be small. OK? So the first direction is going to be easy to prove just using the definition, how we define the Z. And it will be very similar to the proof of the direct theorem for Gowers norms. So as a reminder, our norm looks like this, and we want to prove this. So since we already have access to inverse theorem for Gowers' norm, so it's sufficient to prove that if the L norm is small, then we correlate, then F doesn't correlate with phase Z polynomials. And using the inverse theorem for Gowers' norm, this would imply that the Gowers' norm is actually small. OK? So now we will just look at the inner product with the phase Z polynomials. And now notice that by the definition of Z, if we pick any polynomial of degree less than or equal to Z, we will have full cancellations over the coefficients of the polynomial if we write this summation. And what this gives us is that if we look at the product of the exponentials, it will be 1. And this does not depend on the vector x. And what this tells us is that we have invariance again under multiplication by phase Z polynomials. And using the Cauchy-Schwarz, the similar to Gowers-Cauchy-Schwarz type inequality, we will get the direct theorem. So we basically have that the average of a function is less than its L norm. And since we have invariance under multiplication by phase Z, we get the last step. OK? So now we can move to the second direction, which is the more involved part. So here we will make the assumption that the Z plus first Gowers norm is small, and we are willing to prove that the L norm is small. So the first thing that we will do is we will write the decomposition that was the result by Hamed and Shachar. So it gives you a decomposition of F to F1 and F2, where the F2 has the, so again, another important thing is that we will use the Cauchy-Schwarz complexity of L for the decomposition theorem. So the d plus first Gowers norm of f2 is small, and f1 can be written as a function of few polynomials which are homogeneous and have high enough rank. And the reason that we use the Cauchy-Schwarz complexity of L is that we want to use this Green and Tau theorem to just get rid of f2, which says that if we have a system of linear forms of Cauchy-Schwarz complexity d, then we can actually bound this average, which is now related to our norm, by actually d plus first Gowers norms of fi. And since f2 has d plus first Gowers norm very small, then we can just get rid of. So we know that f2 has small L norm. And since we have triangle inequality for L, so if we know that this is small, now we have to just prove that f1 has small L norm. To prove that, we write the higher order Fourier decomposition of f1, which, as we already seen, it is of the following form. And now we can use the triangle inequality and homogeneity of the norm L to bound the norm of f1 by this sort of linear combination of norms of phase, these exponentials. So what we just saw was that we could bound f1 of the L norm of f1 by this following linear combination. And the next part of the idea of the proof will be that we will prove that either these coefficients are small or these norms are going to be small. So to see this, we will define for every combination, we will define this Q to be equal to that linear combination. And there's two cases. The first case is that this Q has degree less than or equal to Z, where if this happens, since we know that F already has small Gowers norm, then this already implies that these coefficients are going to be very small. And the second case is that we don't have cancellation in high degree multinomials, which means that Q has actually large degree. And in this case, by the definition of Z, notice that Z was the maximum number that the tensor products cancel out. So this would tell us that we don't have cancellation. And now we can use and knowing that these polynomials are of high rank, we can use the result by Hamed and Shachar. And that tells us that these averages are small, which just completes the proof. We just proved that F1 also has small norm. So any questions about the second direction? OK, so just as a summary, we just, for a set of linear forms, we prove that if they are a norm, if they have the norm properties, they have to be of one of the following two types. And we show that for functions that are from Fp to the n to the unit disk in complex numbers, then the type 1 norms are similar to L1 norm, and the type 2 norms are similar to a Gowers norm. And there are a set of interesting open problems, as you already have asked about. So a major open problem is the characterization of norms. So we just gave necessary conditions for these T norms to have the norm property. And we, in fact, actually proved that if the Holder type inequality holds, then that implies already the triangle inequality. So that could be useful, could turn out to be a useful tool. And another open problem would be to get rid of the assumptions that we have, such as, the affine, and this is it. So the linear forms have to be affine, or the Cauchy-Schwarz complexity is bounded. Thank you. Any questions?
Is the Holder type inequality too complicated to write down?
So it is basically similar to Cauchy-Schwarz, but now we have these powers on alpha i's and beta i's that are the real numbers. Now, what we prove is basically that, so if we're looking at an average such as, so what we have is sort of these things, right? And the holder one tells us that if we have two functions, so if we have a function g and have a function f, if we look at this average, g of Li of x, where the power of g is 1, and we actually subtract the corresponding alpha I by 1. So we have this product over i's that are, j's that are not equal to I. And we write just the same thing. And for the Li, we write f to the power of alpha I minus 1. And this times f of Li of x to the power alpha I minus 1. So we show that this average can be bounded by a product of norm of, oh, no, this is, oh, yes, thank you. So now we can bound this by the norm of g times norm of f to some power summation of alpha i's minus 1. Okay. This is a little bit just not nice to, it's not that hard to prove it. So, and I mean, the whole point is that these are not integers, so an idea of using the tensor powers to boost up doesn't work here. So.
Questions?
Thank you.